Okay, likelihood function. Likelihood function can be defined as this way. So let's see, the theta be the parameter, so we will be the parameter, so either mean, standard deviation, that kind of parameter. It doesn't have to be some statistical parameter. You can create your own parameter. x1, x2, 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 x3, and so on, xn be the sample data from the PDF. So we know what this data from the which distribution. So, however, if this the sample data x1, x2, x3 up to xn is IID is independent identical. So independent to each other, and then from the same distribution. With the PDF, and likelihood function will be defined as this one. So basically, likelihood of the one number for one number, this is basically the PDF, probability density function. Since we have a multiple observation, so what is the probability we can get a x1 there's from the PDF, and then x2 and x2 and x3 and x4. But since this is all independent, so we can multiply the probability. Likelihood is not a probability, but it's related to probability. So we can just simply multiply all the PDF function, and that's what we defined as a likelihood function. Basically, if you draw the PDF, this y value is not a probability. Probability is given by the area under the curve, right? When we have the section, and we can calculate the probability by calculating the area under the curve. That's the probability. Right? This is not a probability, but this is actually the density. But we will use this y value as our, if x is given, and we will use this y value as our likelihood. Okay, so one observed value is given, then we can find out the likelihood. And if we have since we have a multiple observation, so we can multiply all the likelihood of each observation. Okay, that's why this is a multiplication, changing by I1 to the n, and you just keep multiplying. Not the sigma is keep adding, right? The sigma is just keep adding, but this pi in the operator means is you have to multiply. So we will define the log likelihood function also. Log likelihood is just apply the log. So this log can be the natural log. Yeah, we will use a lot of natural log, but it doesn't have to be the natural log. Because it's this likelihood is has a multiplication, so we can separate out this multiplication into the summation by applying this log. That's why we will use a lot of log here. This is how we define the likelihood. So we will use a PDF function, and then directly the y value, we will use that is a likelihood. Of course, the probability of x equals x1, very specific number, will be 0 on continuous random number. This probability will be 0. However, we can use this y value. That's what we call the likelihood. Maximum likelihood estimator is since we define the likelihood. So if I have a multiple observation, and our likelihood of observing that observation if the parameter is given. Okay, so this is like a likelihood of observing x1 and x2 and x3, xn given the parameter is given with the given parameters. We can calculate it. Now I want to find out the theta because observation is just observation. You cannot change observation, right? I want to find the theta that maximize this likelihood. That's what we call the maximum likelihood estimator. Okay, so we talk about the log likelihood. So maximum of the log, this is a log likelihood, right? Occurs at the same place as the maximum likelihood. So even though we apply the log, so the maximum here, I want to find out the theta that maximize this function, but this theta will also maximize our log, right? So this will maximize, and this same theta will also maximize this log likelihood. So if we can find what is the theta that maximize my log likelihood, and that theta will maximize the normal likelihood also. So that's why when we look for the theta, you can solve for the using the log likelihood or likelihood. The answer will be the same. So this is one example. Let's see the example. So X is the number of success in 5 free throw. So it's best free throw in the basketball. You can try the 5 free throws. So the possible outcome will be the 0, 1, 2, 3, 4, 5, right? If you success all of them, and you got 5 success, or if you just got 3, 2 fail, then you got a 3 success. So X will be my random variable. That's the number of success in 5 3 row. So X will follow the binary distribution. N is 5, and the P is the success rate, success probability of success. But I don't know what is the probability of the success here. So I'm trying to find out what is P here. Okay. So it depends on our observation. So probability, but here this is not a continuous random number. So actually we use, instead of the PDF, we use a PMF, which is the probability mass function. So function is the given P. If P is given, then we can calculate what is the probability of having an X. So this nx is the same as the n. If you're familiar with this expression, this is the combination. How many different ways we can choose x number of item out of n number of item, and order doesn't matter, right? So it will happen, the success will happen x times, and then the failure will happen n minus x times. And then this is the failure probability, and this is success probability. This is the number of success, this is number of failure. Okay, and the likelihood function we will just borrow the PMF as a likelihood. So here this is actual probability. Now suppose we got the 3 success in 5 trials. So we try 5 times and then actually we success 3 times. So if you calculate the find out the P given X, you can write the same way. Actually, even though this is different, we calculate the same way. Now we apply the log here. Since this is connect to the multiplication here, multiplication, and this is multiplication, we can separate out and by addition, right? Just a log of the combination, and then log p power to the x and log 1 minus p power to the n minus x. And then since this is log, you know the exponent can come down, right? Will be the x log a. So you can bring this x down and then n minus x down, and you got a log, which is this one, log likelihood. Now I want to find out p, right? X is given. Actually, I know what is x. It's a 3, right? Here's the 3. I know x is 3. N is 5. But I want to find out the p, right? Oh, not here, actually. So I'm not looking for the x. X is 3. I'm not looking for n. N is 5 is given. But I want to find out the p. So actually, p is the population value. But I want to estimate that population probability of success using our sample. So this will be the estimator of the success probability P. How can I estimate using my sample? So if you take a derivative here, so this term doesn't have a, so actually the derivative is over P. So what we are take a derivative is actually is over P, because I'm looking for the P that maximize L, right? So doesn't have a P at all, so it will be gone. Because it doesn't have any P, this is kind of constant in point of view of the P, so if you take a derivative, that's gone. And this one, X is just a multiplication of the constant, so you can have X. And log X, take a derivative, that is 1 over x, right? So that's why we are taking derivative over p. So log p becomes 1 over p. So that's why it's x times 1 over p. Plus n minus x is also kind of constant. And log n minus p is 1 derivative of log n minus p is 1 over n minus p. But inside of this log function, there is another function, is 1 minus p here. So I have to find what is the 1 minus p derivative, which is minus 1. So you have to multiply this one too. And then you set it 0. So we are trying to find out when the maximum happens, right? So the slope is 0 here. And then you can find it out which theta will maximize my likelihood function. Okay, so you set this equals 0. Since this is minus, you can set it, this term and this term should be the same. So you can put it in and then you multiply both sides. And what you're going to get is x 1 minus p equals p times n minus x. So if you expand it, it's x minus xp equals np minus xp. So both sides you have xp, so you can just delete it, and then you got the x equals np. So I'm trying to find out what is p. So you divide n both sides, and you got a p. The estimator will be the x over n. Yeah, again, this is a kind of common sense. If you try 5 times and then 3 success, what do you expect the p? What could be the best estimator? It's just 3 over 5. This is pretty intuitive. However, this one has a strong fundamental, the foundation of the why directly we use a 3 over 5. That's actually the good estimator of the population parameters. Now we will look at the same example, so binomial, the 5 trial, 5 free draw, and then 3 success. However, rather than looking at this one event of the binomial random, rather than that, we can consider this is a 5 samples of the Bernoulli. The binomial and the Bernoulli difference is the Bernoulli happens only once. That's why the Bernoulli random variable will have either 0 or 1. But binomial can have a 1, 2, 3, 4, because when we try the 5 times, number of success can be twice or 3, 4, 5. However, Bernoulli just try once, that's why it's either 0 or 1. Since we actually each case is a Bernoulli, so you can consider the one binomial sample. It's same as a multiple sample of Bernoulli. So our case is you can see the 3 success out of 5 is can be we can see this data as a 5 sample from the Bernoulli. So Bernoulli probability formula is like this. This is the PMF again, probability mass function. So we will use this as our likelihood function, right? So same as this one, but we don't observe only one. We observe 5 of the 5 results, right? So we have a x1, x2, x3, of x5. So we have to see the probability of we observe x1 with a given theta, and we have to observe x2 with a given theta, and then we have to observe x3 and so on, right? That is expressed in this form. So if you just write down or write all of this, because it's a p x1 1 minus p 1 minus x1, right? So basically why our probability looks like this is our p should be our probability can be p or 1 minus p. If x is 1, then our probability will be success probability. If x is 0, then my probability should be 1 minus p. That's Bernoulli, right? However, how can I get these things as a one example is like this? Because the xi, here xi can be only 1 or 0, right? If the first one is, if this is a 1, and the later part will be gone, this will be the 1, because 1 minus x1 xi will be 0, so power to the 0 it will lead to the 1, so it will be disappear. It's only this part left over, right? And then since it's a 1, it becomes p, and when x is 0 and this one becomes 1, and this will be the power to the 1, and you have only 1 minus p. Anyway, you are multiplying these things again and again, right? So p x1 times 1 minus p 1 minus x1 times p x2 times 1 minus p 1 minus x2 and so on, right? So if you collect the p and p and p here, this is just like a p x1 times p x2 times p x3, right? This is the same as the p to the x1 plus x2 plus x3 plus and so on. So that's why we can write it is a p to the sigma xi. That's how you got the this term here. And then same thing can happen because 1 minus p, 1 minus p, you can just add up 1 minus xi over the exponent. Now we apply the log to our likelihood function. Then this exponent come down, this exponent come down, and then multiplication becomes a part addition. So you will have this term. Now again, I want to find the p probability success of probability of success that maximize my likelihood function. So likelihood function, maximize likelihood function, and then you can take a derivative. Here, this is just a constant. You come here, and then log p becomes 1 over p, and again this is the just constant is come here, and then same thing is 1 over 1 minus p times minus 1, that's why it becomes minus, and equals 0, and then what you're gonna have is exactly the same result, because you add up to all the, actually this calculation is the number of success, right? So what is this summation calculation? This is the number of failure, right? And then so number of success is 3, and then n is the what? N is the number of trial. So your estimation of probability is 3 over 5. This is exactly the same result, but you can see that when we have a multiple observation, multiple data, then how can we apply the likelihood function? And then you might already seen the why we apply the log, because I want to bring down the exponent, and multiplication will become so positive addition, and then we can handle the calculus way easier. And the advanced better thing is, once you find out the p that maximizes small l, that p will maximize the large L also.